Alright, draft physics video, pretty much. Yeah, I don't know exactly what I'm going to talk about. Just a couple things on my mind, so I thought I would opine. And it might go some overview kind of thing and deal with some of my keywords and vocabulary and whatnot. But things, different things on my mind. The ferrocell thing, for one. Just that fractal woman, if she's still listening to these videos, if she could use the ferrocell with just one light LED, one light source, and see what's produced, that would be helpful in understanding how this thing, how the magnet affects, changes, creates a defect, a visible one. Because clearly there's no effect with just looking at the cell, and until you put a magnet in and that changes the density of the material somehow, and that change in the density changes what light gets reflected or refracted, and still trying to understand what appears to be the curved line. That's all I'm seeing so far. It seems like, anyways. Something like this is happening. The LED is here at the focus of a line that ends up curving, and the magnets would be at this here. So the line is on the back side of the magnet, and it curves for whatever reason that is for that to happen, and that's what's got me curious. Anyway, another subject. Probably should stay with the paper here. Alright, the Big Bang thing. People keep talking. I was listening to some guy who's, talking about the big universe mostly, and how everything's functioning out there. They keep talking, okay, they got this cosmic background radiation, and it doesn't really make sense to me with a Big Bang theory. I mean, as I understand the Big Bang, you have a little compact, something the size of a solar system, let's say. It could be smaller. And all the matter in the universe is in that little space in the form of a bunch of compressed neutrons or whatever. That's how they always put it in the terms of densely compacting things, in the sense that they use the neutron as the example, and just a bunch of neutrons next to each other, in terms of creating a more dense form of matter. But anyway, so you have this thing, and let's say it explodes, or whatever it does, bangs. So you have this bang event, and it's not really defined very well how we could see any background radiation. So the point is that it's hot. Okay, the initial universe is hot. So let's say when it first starts expanding, it's hot. 2,000 degrees Kelvin, or whatever the hell they say it is, hot. And so this radiation is, say, in the form of more like light and infrared and ultraviolet and all that kind of stuff. It's in this higher bands, but we're seeing it redshifted as cosmic background radiation. Now, I could sort of understand this expanding universe argument from the point of view of, let's say you just take two atoms in the Big Bang, one here and one here, and they shot out. Well, they would shoot out, let's say, and as they got further and further apart, they would be further and further apart. Clearly, this distance would keep increasing, the distance between them, as the universe ages. So I can understand the universe is a big, ring of expansion. All the material bits have a certain speed, and so they would end up in the same area, some thickness of locality. Faster bits would be a little further out, slower bits a little closer to the origin bang event. But the cosmic background radiation would be the heat from some earlier point. So if this was 13 billion years here, or say 13 billion here, this is as far as we can see away from us. We're going back further, is where the cosmic background radiation was produced. But the point would be is that radiation is moving the speed of light out this way. And it would be, way ahead of us. I mean, it would have shot past us at light speed, and we'd have no way of seeing it because you can't look at light. You can't look at the light going somewhere. It has to hit you, and the radiation would have hit us way back here. I mean, it would have hit us. It would have gone past us right from the start. I mean, we were always going slower than the radiation, right? I mean, we were always going slower. So it would have gone way past us a long time ago, and we wouldn't have any hint of its existence. So what is the theory there? It just doesn't, I can't make any sense out of it. And even this argument, this one only works in a sense of if you understand us to be moving at some moderate middle speed, and there's stuff going faster than us and stuff going slower than us, then we could look in any direction and still see stuff. But that's kind of seems awful coincidental that there'd be just as much stuff this way as there is this way, in terms of looking, and just as much stuff this way as there is this way. Why is there such an equal amount of stuff surrounding us? Because that doesn't really fit. You would think that looking one way we would see a lot less stuff than if we looked the other way, if there was this bang event. Because where does the consistency come from? So if anybody has a link to any video, lecture, I don't care. I don't care what its source is, what its purpose is, but something that goes through this explanation of how we can see cosmic background radiation when it's really supposed to be origin radiation. And if it's radiation from the origin of the universe, how can we see it when we're moving slower than the radiation? It just doesn't make any sense. And this whole idea of an expanding universe in terms of banging doesn't really work. So if you come up with some other different kind of bang, that is, every piece, you have a universe of things, say 4 things, a lot more things than that, and you just say it doesn't bang, it just expands. So the 4 things get further apart, and then further apart, further and then further and then further apart. You're still going to have a problem creating a history, in terms of, say this was us. We'd still have to be in the middle of something, not to still see nothing this way, or less stuff this way than we would see in the other directions. So you still have this density problem, like where were we in this pile of stuff that expanded? And the argument would have to be we would have had to been right in the middle of it somehow for us to see an even amount of stuff in all directions. So that doesn't really work. And you're still stuck with this. The past is still going to be in a location, in a sense, and you can't evade that in terms of the heat thing. So you can't say that there was a bunch of heat in the past in this kind of expansion, because this kind of expansion wouldn't create any heat. So that doesn't make any sense. And it certainly still wouldn't make sense about how we're expanding faster than the speed of light, because that would be the only way the heat could take time to get to us. This much time, 13 billion years to get to us. How did it take 13 billion years or more for the heat to get to us if we weren't somehow going away from the heat faster than the heat was coming towards us? So again, it just doesn't make any sense to me. So if anybody can point to something that has some, they never talk about this. They always just talk about their mathematical equations and their Hubble constant and some other bullshit. But they never really explain how you can see this signature of the origin event in the form of radiation that's moving the speed of light. how it wouldn't have already gone a lot farther than we have gone away from the origin. That's pretty much, I think, a rational way to say it. Alright, so that's just something I'm pondering. You know, they're so confident, and it just seems, you know, I should have a better diagram for all this confidence. So that's the other thing about so on to the Einstein and bent space and different ways of looking at this. So I've sort of pointed out that you can look at the universe and you can see that the big universe is just a bunch of clumps of stuff behaving kind of simply. It's a kind of there aren't a whole lot of rules. There's not a whole lot of complexity. It's just stuff swirling and banging and colliding, and there's nothing like human in there. There's no dogs walking around in the big universe. There's no complex events, let's call them. It's pretty crude, pretty simple, pretty mechanical. And then we sort of have a model of the small universe that tends to go the same way, in the sense that we know it's all really just about a force goes in, and there's rigid rules about how the force goes out. And they've formalized some of that in simple mathematics, and then some of it's in very complex mathematics because they're trying to calculate how it would happen over time in a complex solar system or something, and that math gets a little more complicated. But it's still it's still simply adding up the influence numbers, just adding up the bits in a way, calculating you put a certain amount of energy in and a certain amount of energy comes out, and it's that simple. And then we can see that in our chemistry, but our chemistry has all this variation in it. So here in this part, this mid-range, whatever you want to call it, between the big stuff and the very little stuff, you have this really complex amount of function. So that's curious, but it's not like, you know, woo-woo. You don't need a religion to sort of understand how that could be a theme, in that you revert to as you get bigger, it takes away your options. And likewise, when you're smaller, it takes away options. So probably another way of analogizing that to something where the limits exist, because the big things can average things out so much that they take away all the little vibrations, and the little stuff isn't technically, you could almost argue, vibrating. It's just moving and being influenced, just on a different time scale. Alright, so that's the first thing you observe about the universe, is that at the biggest end it's simple, and at the smallest end it's simple, and it's only in this middle that it's messy or complicated or nuanced and all that kind of stuff, where there's a whole lot of influences, I guess is the way to say it. It's the individual bits are just individual bits. They're just one little identity, and they're just influenced by the stuff that influences them, hits them. They don't have any internal motivations or ambitions or any of that kind of stuff. They're just kind of simple. So if the outside hits it, it goes that way. If it does this way, it goes that way. And it's really just the amount of this little stuff. There's so much of it. And the little stuff ends up banging into a lot of other little stuff because there's so much of it. It's so crowded. And the big universe has like the opposite problem. It's so uncrowded that there can't be any of that, you know, complex interactions between things. We can't interact in any physical, hard way with stuff 13 billion light years away or ago, because the only thing left behind is, you know, little photons flying off of it. So the great distances we're separated by eliminates any chance of any influences that are meaningful. And so that's why there's so little complexity. So I guess you could almost argue it that way. The little stuff is so dense that it can't avoid creating what we consider our mid-range complexity. But from the little bit's perspective, it's really simple. I just go where the things hit me. And But when you put a bunch of that together, that noise is what we're experiencing, that very complex layer of interactions. And then the big universe, it starts to get less noisy because there's less interactions. The big stuff doesn't interact with each other much. All right, in a primary way. It only interacts in this very subtle transmission of a few photons kind of way. All right, so a key thing I've been thinking about is, with this idea of action causes reaction. First you have to have the action part. And that gets me thinking about this whole idea of inertia and motion. And so I've sort of explained that there's only one element that has true perpetual motion, and that would be this element of what we consider of the force of light, the electromagnetic spectrum. Anything in that spectrum, we get it. Now, the other stuff we aren't counting as part of that spectrum, gravity and magnetism, but that's all part of the same. It's the same stuff. It's the same energy going in. So we certainly count it as energy going in. We just don't account for its creation. So certainly if I put a magnet next to a jar full of stuff, the physicist will concede that the magnetism is going to affect the stuff in the jar. It's an influence, and it'll have an effect. It's energy in a sense. Especially the movement of the magnetic field into the jar is clearly an energetic. It's as if the magnet's being pushed into the jar. It's an extension of the magnet in the physical sense, to them anyway. They'll at least concede that the magnet is physically represented by its matter, but its field is an extension of that matter, and the field counts as energy when it's moving. All right, not unlike physically pushing matter into the jar. So even though nothing goes inside the jar that we see, I would argue rational physics would concede that there's energy going into the jar from the magnet. And that, energy is the trick word. That because the magnet has the capacity to segregate the polarization of this energy that's in the field already. So it's energy that's going in the jar anyway, but by segregating it, you make it more effective in terms of producing an effect. But it's really just the movement that you're really counting. You don't see the movement if the material isn't magnetic. So it's sort of a quandary, because I could argue if I take a flashlight and just push it next to the side of the jar, it's not magnetic. But clearly it's doing the same thing as the magnet in the sense energy is going in, energy is coming out, and energy from it will go into the jar. It's almost like counting the photons that are reflecting off of the object and even considering them something that the thing itself produced, but it didn't really produce it. It's just a reflection of light. But anyway, so that's why the words energy it's a messy word, because much of what we see as energy is merely creating a specific circumstance for which the other matter is reactive. So just like our skin is more reactive to ultraviolet light than it is infrared, and it'll tan, it'll react. It's not that people think it's because it has more energy, but it's just because it's more sensitive. It reacts to certain frequencies more than it reacts to others. So it's sometimes what we see as energy isn't really seeing it for what really went in. It's the specific stuff went in that the system is reactive to. It's like I can throw this pen on the piece of paper and it doesn't catch it on fire. But if I put a lit match on top of it, it catches fire. I mean, there's just circumstances. You know, it's not like the match weighs more, the burning match, or some other physical amount of energy. It's just that it has a circumstance where it's creating heat and pressure that will enable the rest of the paper to have the same chain reaction. But if I drop them in water, you know, it's a different reaction. So it's really not about the energy of the thing moving into another thing. It's how it's moving into it and what part of it is, what form the radiation, what form its effect in the universe is in. Still not a great way to say it. Alright, anyway, back to perpetual motion. So if we could agree that everything's based on this cause and effect, like something has to hit something else, there has to be a physical interaction of some kind. And a lot of people won't agree with that, but I'll just say, let's just agree that whether you call it physical in the physical sense, or whether you just understand it as a quanta, or you just understand it as an event, there's a thing that can be identified that has properties, that's moving, say the speed of light, and it has to hit something else for something to happen. You know, the spooky action people won't think that's even necessary, but we'll just forget about that. My point would be is that how we calculate the universe, the strictest physics, does sort of see it that way, that you have to have quanta in before you can have quanta out. You have to have quantity in before you can have quantity out. Something has to go in before you can have something come out. And so the idea is that the bits that have this motion, all these little, the element of the photon, represented as anything from radio waves to gamma rays, and then I would extend that to the stuff that makes gravity and magnetism. But see, that's when I say extend it to that, it doesn't mean anything to people who are still thinking gravity is some sort of geometry equation, or that magnetism is some sort of virtual energy transference. You know, the people who just don't want to concede that those are real forces, just like the electromagnetic spectrum. And the only difference is they're not at a frequency. I mean, for magnetism, the simple difference is it's polarized. You know, magnets just segregating, you know, the A from the B's, the electron sensitive from the proton sensitive, the round from the square. And by doing that, we'll affect electrons and protons dramatically by segregating the force they're sensitive to. And so it's not at a frequency. We can't see it with our eyes, but we can see the effects of magnetism. And gravity is doing the same thing. It's just that the segregation isn't as strong, and therefore the effect is much weaker by mass. It's not much weaker by distance. I mean, if you think about how far away the Earth is from the Sun, and took a proton and an electron and put them that far away, you know the proton isn't going to have much to say to that electron from that distance. Their force is going to seem very weak. All right, that's sort of relevant because, in theory, gravity is a subatomic force, and the real things communicating between the Sun and the Earth are the elemental bits in the Sun, the protons and the electrons, and the protons and the electrons in the Earth. They're really doing the communicating. And that's a very long distance they're communicating. But anyway, but the real difference on the nuclear level and the Earth to Sun level is the inverse square law, because the small bits don't do the inverse square problem. They don't do the circular spherical radiation thing. It's much more personal, mano a mano. So all right, I really don't want to get into that. So my argument is all the motion that exists is the motion of that force bits, and that the only time you see something else move is because it's acquired the force bits necessary. They've gone into it. They've actually physically gone into something, and it has an imbalance in it. And as long as it maintains that imbalance, it will continue to move in whatever way it moves, and it won't stop until some other force acts on it, as Newton would say. Now, in this environment, under pressure from air and the atoms in the air and the friction and all the other stuff we have here, you can't just say, well, look, I put some force into a pen and it'll just keep rotating. It won't happen, because first gravity is going to do that and ruin the whole experiment, because it's dominating the energy equation. It's creating a whole bunch of stuff hitting this side of the pen, and not too much stuff hitting this side, much less. And so the pen does that. No matter what I'm doing force-wise, the forces I'm imposing are a small fraction of the forces hitting this pen, even when it's perfectly still. So there's a ton of force hitting everything here in this experiment. And so this is just a tiny bit of noise in a field of already existing forces that are interacting with each other. And so that's why I can't do any experiment here on Earth that isolates my force influence. I can't just tap the pen and make it spin in space. So obviously I could do that in space, though. In space I can do all kinds of experiments where gravity is to some extent neutralized or balanced by free falling. So by constantly falling, actually falling, they can continue to do the experiment because nothing ever hits where it's falling to, because what it's falling to is also falling. So it's in a perpetual state of falling, which means it's as if it was in free space and there was no influence on it. All right, so yeah, it's just kind of a key thing, and so I would contrast that to the Einstein theory, that basically, and quantum mechanics. So there's like two separate things. So they put gravity in a separate category. It's just obeying geometry. It's not a real force. No energy involved, really. And then you have quantum mechanics that has turned all of the little bits that I would argue with the electromagnetic spectrum, they still concede that to be quantizable and elemental, but the whole flood of stuff that would come out that would create magnetism, like I'm saying, is not counted as real energy, as real little bits with a velocity, real force hitting stuff. So quantum mechanics has both of them deny the existence of the force that creates gravity and magnetism. So even though quantum mechanics covers magnetism, it denies the existence. It doesn't have a carrier for the force. It calls them virtual photons and just says, forget it, we don't bother with that. And then bent space, or geometry projection, or whatever you want to call it, movement through geometry, Einstein's whatever you want to call it, space-time, provides no mechanism. So they've kind of broken the ingredient part, because they're not conceding there are ingredients that create the motion of the Earth towards the Sun. There's no I didn't have to put something into the bowl in terms of a force to make it happen. And likewise in quantum mechanics, you don't have to put anything, there's nothing going into the bowl in terms of they accept the effect of the magnetic field, but they don't accept it having any material mechanism. They accept that it's energy, they just don't accept that it's sourced. I don't know how else to say that. So really I'm getting to is that all the motion is created by the little bits moving the speed of light. And even though this doesn't look like it's moving the speed of light, and it isn't, the point is the little bits that are making that motion are the energy equation, the energy that pushes this pen down. The force is moving at the speed of light. It just can't make everything in the pen do that instantaneously. So everything in the pen takes time to push all of the bits inside the pen, and that time is going to be its acceleration. And its acceleration will keep growing and growing as long as you don't have any atmosphere or other thing to get in its way. It'll just keep going faster and faster and faster if you give it a long enough time to fall. It'll have no terminal velocity. Terminal velocity, that is the fact that this, if I did throw this pen off a building, it would get up to maybe 50 miles an hour and it would go no faster. Probably less than that, probably 30 miles, 20 miles. It wouldn't be able to go any faster because the air resistance would create more friction than the force is creating motion and the turbulence, so to speak, from that air resistance. So it would never gain any more speed. It would just go 20 miles an hour forever if you could do it forever. Whereas if there was no atmosphere, the pen would eventually go, theoretically, if you could let it fall for a very, very long time, it would go as fast as the speed of light. It would just keep accelerating. Every 10 meters it would just keep getting faster and faster and faster and faster. And so, so begins the subject of black holes and event horizons and all that mush. But I don't want to get into that nonsense. But the idea is that the speed has to be absorbed. And there's two ways you can absorb it, in this kinetic all way, where you just transfer all the force. The thing that hits it stops, and this thing gains all of the energy. There's no rebounds, there's no elasticity, there's just a solid transfer of force and motion. And then there's the ones that have to soak in, so to speak. The force has to soak into the matter and alter its condition through some process that takes time. And but anyway, so the point is the pen moves slower than the speed of light because it's not changing everything inside of the pen. It's only changing the percentages, and so it's giving it more this at any one moment, and then it has this, and then this, and this. And we're also fooled because the time scale, we function on this very slow time scale, and this stuff that's affecting this pen is happening in billionths of a second or trillionths of a second, very tiny time scales that all their action, their whole lifespan, so to speak, their whole interaction takes place in. So anyway, the real point is that the perpetual bits, perpetual has it means more than just going forever. It means that whenever one of these things, these energetic bits get into a bowl, get into a system, that you have to account for it. I mean, it's always in motion, it's always doing something while it's in there, and then if this stops doing stuff, then you have to explain where it went. So if the energy goes in and you measure it, it's okay, I can see this thing's hotter because it has this little bit that went in. Well, that heat has to, if it cools, then you have to account for where it went. And where it went is to affect some other pen. You know, some other pen is now moving. Some other thing is now moving. And then that will dissipate it and it'll go somewhere else and that thing will be moving. And so all the motion is just redundant. It's all the same little bits that are causing this motion. So theoretically, I mean, Ben Franklin could be sitting there with his quill, you know, thinking about the quill and how he can wiggle it in his hand and what's causing it to move, and the exact same little bits that are making it possible for me to change how this pen moves are exactly the same bits that, you know, move Ben Franklin's quill. You know, and they just did a whole bunch of stuff for the last 300 years. They've been flying around here in this heat of the surface of the earth, bouncing around off of things, getting captured by things, moving, you know, different things, different places. And so just like the atoms, you know, they're all reused. All the energy is reused. It's all recycled energy. There's no, you can't avoid recycling. It's what energy does. So it's just like these atoms were dinosaurs at one time. You know, the little bits inside of this pen, you know, these hydrocarbons. I mean, these were literally stored in the ground for a while, these atoms. You know, a long time actually, hundreds of millions of years. And then they got brought back to the sunlight again, and they're out in the real world again. And they might have the potential to be alive again, do all kinds of things again. But it's the same thing for energy. Energy does the same thing. So, you know, you eat food and you release it as lots of byproducts, motion, and also a lot of heat. All those little bits get released again. So, you know, the sunlight, it's the plant, you know, energizes it. We eat the plant, we grab the energy, and we radiate back out as heat like the sun did. You know, back into the form of electromagnetic radiation. And that's what all this stuff is constantly doing. And to me, that equation of understanding that, yes, that's what's happening with gravity and magnetism. That it's the same little bits that are moving the Earth. The Earth is moving towards the sun because there's stuff hitting it and it's absorbing it. It's getting hit by it. The radiation's going through it, and it's grabbing some of it. Some of it's staying inside of there, warming it up and you know, and energizing it, and it's moving it slowly, not the speed of light, but it's adding a bias in the direction towards the sun because it's getting hit from more stuff outside than it is on the inside. And it's absorbing more stuff from the outside going towards the inside. And that explanation is so much more reasonable than some, you know, the math, the geometry written on a piece of paper. You know, the converging lines I drew on a piece of paper are telling the Earth, this is all the Earth needs to see. See, it sees a converging line, and it says, oh yeah, I got to follow that converging line. You know, that's not an explanation. It's not reasonable. And it doesn't fit with everything else we see and know about why things do what they do. And we know you have to put energy into the battery to get energy out of the battery. You have to put energy into the chemistry, you know, to create a rocket. You have to use energy to create the fuel, at least to purify it. But the chemical energy was put in by the sun originally in the form of the oil that we are refining into rocket fuel. But even if you made the rocket fuel out of something else, like hydrogen, you still had to expend energy to, you know, collect your hydrogen, and separate from all the impurities to be able to create your rocket. And what's to say about that? Yeah, I don't want to get into an argument. I don't want to get into chemistry, because chemistry is chemistry is very interesting, just in the fact that you can, you have different. It's like the nuclear bomb thing. I was talking about that in the other video because Ken Wheeler brought it up and stuff. And some nuclear bombs are doing the breaking the atom thing, and it's not the breaking of the atom, that's letting a whole bunch of stuff go out. It's just splitting an atom into two things, that are stable. So you take a big atom and you make two smaller atoms that are stable, and you just have a lot of stuff left over. And so the bomb is just the little stuff left over. You didn't even break the whole atom and release everything. You just broke it into two pieces that were 80% as big as the original piece, and you got the 20% of leftovers. That is the energy. So that's why bombs can be made out of different things and get higher yields, is because you can create byproducts that are smaller, and therefore you have more wasted bits, and that is more stuff to explode. More energy, more free energy in terms of you doing your fission thing. And then the sun, when it's fusing, is doing the same thing in reverse, in the sense that it's taking two little bits and smashing them into a whole bit that's only 80% as big as the two little things. So the two little things are 50-50, and you only get 80 out of that 50-50, and there's 20% left over again that's released as free energy. So it's not like you're, well, anyway, so the chemistry is obviously kind of reversible, like which end is more energetic. And it really just has to do with this pressure argument, that the stuff under more pressure is the stuff where you'll get more energy out of it, more condensed bits. And you could argue that the neutrons are condensed bits, and that's where the real energy is coming from. I could argue that. I would argue that. But clearly there's a whole bunch of investment in the energy that is obviously keeping the atom together. And that same energy is the same energy that's in this magnetism and gravity thing and the electromagnetic spectrum. They're these little bits. And you're getting rid of a whole bunch of these necessary little bits that are inside of the atom when you make two smaller atoms. Probably no right way to say it, but not exactly what I wanted to go for. Alright, so we kind of got to the point that, alright, so the perpetual thing, the idea that the energy is just always being just transferred, and that sort of gets to this whole space argument and entropy and the fact that the universe is going to slowly die, is because it's radiating heat to places that can't be places, at least by our understanding of the universe and having a certain size. The radiation's leaking out to places that can't be places, that aren't going to be places where they can bounce off of. So logically you'd say it has to die because it's losing the little bits that are, it's like one of those little droplets of oil that was, say, a dinosaur, and it's liberated into a pen, and then it's liberated into rocket fuel, and then it shoots into space, and then it flies off into some dark region of the universe, never to interact with anything ever again. You see, it's lost. It won't hit another pen ever. And so in that sense it seems impossible to imagine a universe that wouldn't die a heat death, because it has to be radiating beyond its, to the future, and it's doing it at the speed of light, so there won't be anything there. It's going to get to the future before we get there, so it can't possibly influence anything in that future, because it's going to get there quicker than any material thing will ever show up to meet it. So it just seems logical to say that the universe would have to suffocate. I mean, just die a slow death from lack of energy, because it expels all of its energy eventually. So these diagrams they have just don't really make sense. So you'd have to concede that even after 13 billion years, we should be a lot colder than the universe we're looking at. A lot colder. It doesn't seem like it's that much colder. So that part doesn't even make sense. The universe 5 billion years ago doesn't look that different. And it should look different. A lot different. Because we're a lot colder, reasonably speaking, because of all the energy that's just, leaving town, and it'll never come back. So I think the story has to be there's more to the story. And so their confidence in this Big Bang and in this time evolution, I think it's just another one of these misplaced, too confident on too little evidence. And they haven't answered, lots of questions, and they haven't even sought those questions. They don't even seek to be tested, and they do exactly the opposite. They evade anyone testing the veracity of their evidence, saying, "Show me," just use excuses to evade those details, or they'll just cite a name and a 1984 experiment and say that's all they need. You do the work of finding out whether the experiment has some holes in it, or gaps in reasoning, or wrong assumptions. So, where else do I want to go with this? So anyway, this is just all stuff I'm working on. Just basically just got it in themes and ideas, trying to figure out how to get it understood that gravity, magnetism, light, and time is just a function. So I didn't even mention the time part of space-time, but there's absolutely no rational reason to include time and connect it to gravity or any other force, or magnetism. I mean, they don't call it magnetime, or light time. It just doesn't. There's no need, because the fact that that clocks are vulnerable, that our measurements of time are vulnerable, doesn't change the fact that light's not vulnerable. Its speed is reliable, and so they just ignore the fact that it's always, in all the contexts that we can do real experiments